Okay, so today's chapter is all about color. Color that we see depends on the frequency of the light. So here I show light increasing in frequency from red up through yellow, green, blue, and violet being the highest frequency. If the frequency of light is lower than red, then we can't see it. It's not really light. It just looks black. And the name for that kind of electromagnetic radiation is infrared. If the frequency is higher than violet, then that's called ultraviolet radiation. And again, it looks black to our eyes. And this lambda stands for wavelength. The speed of light is generally a constant, so if the frequency increases, that means wavelength is shorter. So short wavelength would be this violet, longer wavelength would be red. And just to give you the numbers, 0.4 microns, so that's 0.4 millionths of a meter. That's about half of a thousandth of a millimeter is the wavelength of violet light. The wavelength of red light would be about 0.7 microns. Again, less than a thousandth of a millimeter. So here we have a red ball that's illuminated by white light. So what we see is the reflected white light, but since it's red, it's actually absorbing out all the colors other than red, such as green or something, and it's reflecting red. If we just shine red light down onto a red ball, it reflects red. And if we shine green light onto a red ball, well, there's no red there to reflect, so it would look black. So the color of an object depends not just on how it reflects, but also what kind of light we're shining down onto it. Here is an example of selective transmission. So this is stained glass in the Great Hall in UC. And what it's doing is it's absorbing all the colors other than blue and selectively transmitting blue light. So you can also have mixes of colors. So here's the sun, and this is what's called the solar spectrum. It's a graph of brightness versus frequency. So the sun emits some infrared, the sun emits some ultraviolet, but most of what the sun emits is visible light. That's why our eyes have evolved to be sensitive to visible light. And somehow this particular mix is what we call white light. So we have these cones, 3 different kinds of cones in the retinas of our eyes, and they correspond to being sensitive to these 3 different regions of this solar spectrum called red, green, and blue. So this leads us to the additive primary colors, red, blue, green, and they all correspond to stimulating different parts of our retina. And so if you have like this screen that you're looking at, it's a mixture of lots of little dots that are all either red, blue, or green. And when you mix those all together, they're all turned on, it looks white. If you have different mixtures of red and blue, it might look something like this purple. If you turn on the reds and the greens, you can get yellow. And in fact, by just adjusting these 3 different amounts of color, you can simulate any color that our eyes can see. So here's a golf ball illuminated by red and green and blue light. And you can see these shadows are, I guess, what are called the subtractive primary colors. So this sort of cyan is the shadow that's blocking out the red light. This magenta is the shadow that's blocking out the green light. And this yellow is the shadow that's blocking out the blue light. So if you have a mix of all the frequencies, 4.3 up to 7.5 times 10 to the 14 hertz, then that'll look like white light. If you take out all these sort of higher frequencies, then you'll just get red light. If you take out the highest and lowest frequencies, you get green light. If you take out all the lower frequencies, you get blue light. So yellow light is kind of a mix of red and green, as we said. So if you take out only the very, very highest frequencies, that's yellow. If you take out only the very lowest frequencies, that's cyan. And if you absorb out just the middle frequencies and leave the very lowest and the very highest, you get magenta. So when you look at a piece of paper, you're looking at reflected white light. And what ink does is it absorbs out certain frequencies. And so when you buy toner cartridges, you buy cyan, magenta, and yellow. And when it prints, it puts these inks on, which put the pigments down, which selectively absorb particular frequencies. So there's the magenta image, then you overlay on top of it a yellow image and a blue image, and when you combine all these, you get this color image. And it turns out, practically speaking, that it's difficult just using these inks to get a nice deep black. So we also purchase just black ink to kind of deepen the color and make it look more real. So why is the sky blue? Well, when you're looking at the blue sky, you're looking at scattered sunlight. And so when sunlight goes through the air, it encounters nitrogen and oxygen molecules, little particles that are smaller than the wavelength of the sunlight. And it can scatter that radiation. And this is called Rayleigh scattering. And this kind of scattering is more likely to happen at higher frequencies and less at lower frequencies. So this scattered light that comes into your eyes has sort of a changed color. And if you look again at that solar spectrum, the red line is the real solar spectrum, which we would call white if we were looking right at the sun. And this blue line is what tends to get scattered by our air. So as you can see, up in the sort of lower frequencies, the red, it's depressed, and so less light is scattered at red frequencies. At these violet frequencies, or blue, you'll get more scattering than you would normally from just looking right at the sun. So the whole effect of this spectrum is that it looks kind of blue. Why are sunsets red? Well, it's the same kind of thing, except what you're doing here is you're looking at what was not scattered. Light that is least scattered is light that are of lower frequencies, like red or orange or yellow. And that travels better straight through the air. So if you're looking through a lot of air, like at a sunset, this greatest path of sunlight through the atmosphere, then the sun looks kind of red. Why is water greenish or blue? So if you go into the Rockies and you look at these lakes, you get this amazing, nice blue-green color. So these lakes are fed by runoff from melting glaciers, and it contains lots of silt called rock flour, which remains suspended in the water. So these tiny scatterers tend to, again, scatter the higher frequencies more so than the lower frequencies, and it gives the water this beautiful color.